Hello, my name is Iakymchuk. I am from Sorbonne University. I am also associate professor at Umea University. And today I would like to present to you a general approach for reusing reproducibility of iterative solvers. An example of BiCGStab. I will begin with motivation. So we have been working on reproducibility of Krylov type solvers. So we begin with preconditioned conjugate gradient, and we just studied it. And what we did was we conducted a couple of runs using MPI implementation. So we had only message passing implementation. We ran it on a cluster where one node is composed of 48 cores, and we compare execution on one core and on 48 cores. So this table actually shows the residual on every iteration for the example of 3D Poisson's equation with 27 stencil points. What we can see is that there is deviation between computation in terms of residual, and we can see that the deviation is actually progressing when we proceed with our computations. On the other side, we have also implemented the same solver using MPFR library, and from one execution to another, MPFR was delivering accurate results. And condition number here we set to be 10 to the power 12. So this is one example that was sort of motivating us to jump in the studies, to start with preconditioned conjugate gradient, and then we also notice we started with different matrices, for instance, from SuiteSparse Matrix Collection, a matrix called 0K with condition number 10 to the power 9, and we observed also when we use different implementation for non-deterministic variant using MPI plus OpenMP on different clusters. So we observe that number of iterations can also differ. We explain this in the article. We also have conducted a couple of studies on this, so MPI plus OpenMP, but also we compared with Daiichi Mokunoki and the other Japanese researchers using EXBLAST approach and Ozaki scheme. So that was nice, and then I came with an idea. Okay, let's try to generalize it, because Krylov type solvers have the quite similar ideas, and let's see what we can achieve if we will try to sort of create a general framework. So this is an idea of this article, to provide you with presentation of this general framework that we somehow implicitly used in PCG solver. And I will begin with introducing you to computer arithmetic and the issue of reproducibility, or rather non-reproducibility. Then I will speak about this idea of framework, and I will focus on how this framework can be applied to BiCGStab method. So BiCGStab method works for non-symmetric matrices. So it's actually, by doing this, by covering non-symmetric matrices, we can cover sort of a class of Krylov type solvers for different cases, symmetric and non-symmetric matrices. And then I will conclude my presentation and provide future work and future directions. So in terms of computer arithmetic, we are dealing with approximation of real numbers. So we have some representations that we have to chop at some point, and obviously we have different rounding errors and rounding strategies. Usually we are talking about rounding to nearest, so we get the best of our approximation, the closest we can get. But since we have this rounding of errors, we can have we can lose some properties, mathematical properties, like associativity. Commutativity is still there, but associativity is lost. And this is an example that I always show. For double precision, we can do the same example for single and half precision, just changing the power 2 to the power how it works. And then what we see is that we get from one side very small number 2 to the power minus 53, so machine precision that is not equal to 0. So the message here that I would like to give you is that although we may have that floating point computations depend on the order of computations. And obviously, when we have this parallelization, which we are talking about, then we may destroy this order because we cannot preserve it. So we split the task, so like divide and conquer method. So this is pretty much the idea. We split and then we join. And that means that the order will be will be destroyed in such case, will be modified. And the other message that highly optimized libraries, highly optimized solvers that try to feed, like doing this optimization from high performance point of view, try to capture architecture, may lose these properties of consistency in terms of numerical consistency. Performance would be there, but numerical consistency can be damaged due to on the pace to the performance. Then reproducibility is actually ability to obtain, how we say, identical and accurate result from one run to another on the same or different platforms, independently from parallelization strategy on the same method. And we have been working there for quite long, and we have developed EX Plus library, like exact, fast, accurate, and reproducible library, and we begin with parallel reduction. So parallel reduction is obvious things that you will start, like parallel summations. There are many works on that, and recently, for instance, Marco Lange presented AAA summations. That's actually quite nice idea, but we were working from a different angle. So our idea was to try to have preserve every bit of information and try to obtain reproducible results thanks to that and thanks to correct rounding. And we engage in our approach two existing solutions. One is collision accumulator, but we modified it. So in collision accumulator, we have a projection, a vectors that sort of represent a projection of on the entire set of floating point numbers, and then we decide where a number should go depending on its exponent. So when we get number, we extract exponent, divide number in two, and then it lands into the two different digits in the vector. So digit is like an element, and each digit has some margin, like 8 bits for overflow and underflow. But this is a bit costly because it requires 16 flops and indirect memory access and storage in the memory. So the other more attractive approach for high performance computing, because we are sort of fighting for every bit of performance, is actually floating point expansion. It's like short array of doubles or any precision and error-free transformation, thanks to which we can keep and preserve every bit of information until the capacity of this FPE is sufficient. And there are two good approaches for that, called to summation and then fast to summation. So when we want know order of our input values, then we can employ fast to summation. But if we don't, we use to summation. I believe you are familiar with that. So this one costs us 6 flops. This one costs us 2 flops. But we need to do a comparison, which may not be good for GPU because we will introduce branching. Then we sort of created this algorithm, this structure, the schematic algorithm, where we try to use as much as possible FPs with error-free transformations, and then every thread can be independent. We don't sort numbers, we just assign them randomly to the threads, depending on the parallelization strategy. So sometimes we use dynamic scheduling, sometimes static scheduling, and so on. And then we crunch these numbers, and at the final stage, we flush to super accumulator, and then we round to double to desired precision. Sometimes we need to sort of flush in the intermediate stage when we see that the accuracy of floating point expansions is not sufficient. We made it this approach suit well and tune it well for CPUs, GPUs, and Xeon Phi. And thanks to this sort of keeping every bit of information, we were able to get bitwise reproducibility. Now, let's take a look on the solver. So this is the approach that we want to employ. And now let's take a look on the general Krylov type method. So we have AX equals B, where A is symmetric matrix or non-symmetric, and B is right-hand side. And usual schemes that we have some loop when we do computations where tau would be residual, and we try to sort of get our computations in such a way that it will converge, and then the residual would be sort of shrinking in such a way. And then a couple of common operations that we have is like sparse matrix product. We have which is not presented here, but we have also dot product. XP application of preconditioner. So XP would be scaling a vector and so on. So sparse matrix product is over here. So here we sort of split operations and try to map them to kernels from BLAST library, usually how it works. And then we take a look on communication. What kind of communication we need? Because we parallelize, we divide our computations. So we need different processing units, either tasks or threads, to talk to each other. And communication can be different from different needs, but usually we need to employ all reduce. So we conduct dot products individually on each task or process, and then we perform reduction in order to reduce to one single result and then distribute pretty much to every computing unit. With application to preconditioners, it depends on what kind of preconditioner we want to engage. Sometimes it's just simple, like Jacobi preconditioner, or sometimes can be as complicated as ILU 0, incomplete LU preconditioner. So this is a scheme. And then using this scheme, we pretty much can map a different Krylov type method. So it could be that a number of invocation of kernels doubles, or some perturbation of them is there, but the names of those kernels are pretty much fixed, and there is nothing sort of new. It could be also that we try to glue a couple of kernel invocation, and might be we can use, instead of +1 or 2, we can use higher level in order to get better optimization. This work has been done nicely by Daiichi Mokunoki in the Ozaki scheme version of PCG. Now, let's take a look on preconditioned BiCGStab method. So what we have here is on the right-hand side is a bit messy figure, is a representation of algorithm itself and mapping to the BLAST kernels. On the right-hand side, we have mapping to the communication of the same algorithm. So when we look here, so we have different operations. We begin with SPME kernel, so sparse matrix multiplication, which is actually crucial kernel because it eats a lot of computations, but also it's a bit complicated to parallelize, etc. There are also many different strategies and stories how to do it. Then we have dot product XP dot product plus SQRT, because we need to compute our residual, to check conversions, and we have XP, we apply preconditioner, and pretty much we begin the story again. So we have two products and so on, and not to begin, but we extend. So compared to, for instance, PCG, we have almost 2 times more operations, 2 times more invocation of SPME dot products and so on. We also apply preconditioner 2 times in this solver. Now let's take a look on the communication. In terms of communication, we may use or may not use depending on the implementation. Altogether, we were using it in order to collect the vector, and because slices of matrix were distributed between different nodes, and then we conduct our all reduced computations in order to get our results. When we see here all reduced 2, it means that we try to glue 2 dot products into and pass the result. So pretty much invoke all reduce only once in order to save a bit on communication. So this is pretty much the scheme. And now let's take a look to see, or actually narrow down where the issues are, and as well how can we tackle them in order to reassure reproducibility. So there are pretty much 3 sources of non-reproducibility. The first one, and the obvious one, would be parallel reduction, and parallel reduction occurs in dot product. So when we have dot product of 2 vectors, and then we need to apply MPI or reduce there. So I speak about MPI. It can be different all reduce strategies depending on the programming model used. Then we may also have compiler or auto replacement. So when we have a situation AX plus B, A times X plus B, then compiler can replace this operation in favor of FMA. So and this occurs in XP. So in order to avoid this, we compile with we use explicitly, we invoke explicitly FMA, and sometimes it could be also the situation such as SPME, that we may have this operation A times B plus C times D times E, and here compiler has more freedom to decide how to tackle this operation. So the overall idea is actually here. We want to have deterministic path. Deterministic path in such a way that we will know how instructions are executed. We are sure that compiler will not interfere. And in order to have this deterministic path, we combine arithmetic solution, reorganization of operations, and some sequential execution. So reorganization of operations pretty much follows this 30 years old guide from David Goldberg on computer arithmetic. So, and we also aim to have this lightweight or lighter approach. Obviously, we use FMA for XP. We also make sure that we don't screw our computations in SPMV. So we explicitly we conduct one of multiplication, and then we explicitly invoke FMA. So we are sure that we choose one out of 3 possible paths. And then in order to have a reproducible and accurate dot product, we use X plus approach that is actually I presented to you, but we also sort of rely only on FP of size 8 with early exit in order to be sure that in order to derive more lighter version. So it depends if we know our matrix is well conditioned, if you know many things that we may rely on this lightweight approach. Then during the initialization, usually we were taking DS identity vector, and then we were sort of scaling it by inverse of square root of n, where n is number of rows or columns. And here the problems can occur because it's better what we experimented. It's better to just immediately do this multiplication and only then scale the product, the result, because nothing will change here. But what we have seen sometimes, for some examples, we can get a lower number of iterations by up to 7%. So it's actually good to think. So good to postpone division until really when they are needed, and to do other computations on the fly. Now, obviously, the cornerstone of here is dot product. So dot product, we have EX plus solution, and it can be seen as virtual. It can be built upon a summation, exact summation, and two product. Two product is another FME that takes 3 flops. So thanks to another EFT, error-free transformation. So we do our multiplication, and then thanks to FMA, we can get our error here. In this code, I will focus on floating point expansion, how implementation works. So we have our local dot products of size nk, and we perform these 2 products. Then we accumulate a result and errors, and we glue together to floating point expansions. We conduct MPI reduction, and we round to the target working precision. In order to accumulate expansion one to another, and we also create this routine that actually performs pretty much chain of 2-sum operations in order to get results together, a result and error into one vector of doubles. Now let's speak about results. So we have the strategies, we employ the strategy, we tune them, we try to squeeze them as much as possible of performance. And here I will be focused on results on matrices from SuiteSparse Matrix Collection. We are working right now in order to have some generator as we had for PCG, but let us be focused here. So this table is a bit complex, messy, I would say. A lot of information is there. So we have matrix, whether we apply or not, preconditioner, condition number of rows, columns, and then we have number of non-zeros. Then we have residual at the beginning. Then we see how many iterations depending on the number of processes we used. Then we have true residual computed, and then we have BiCG non-reproducible standard implementation. Just to be clear, we did our implementations by ourselves, and then our reproducible BiCGStab. We in the next slides we'll be focusing on these 3 matrices due to the condition number. So we have very well condition number, a mildly ill condition, and quite a bit ill condition matrices. Then as you can see on number of non-zeros, we are not getting too much non-zeros. So it's actually, this was one of the stopping criteria for us, that we were not able to go to the full scale, because otherwise we just simply will not see the math. We will only measure communication. So, and the tolerance here was 10 to the power minus 6. In terms of convergence, what is important here is that to notice two things. So, for instance, number of iterations. That what actually I would like to point you out. So here you can see number of iterations on one and with 1 and 8 processes, and then we can see number of iterations that we get slightly better in number of iterations. This is actually quite nice, but usually we are pretty much in the same scale. And so on. It's the same scale, but in terms of accuracy, we always get intermediate and final accuracy, intermediate and final result reproducible independently on the number of processes involved. So let's take a look on sort of convergence history or residual history for matrix FS, and it has almost 6,000 non-zero elements, and we use it without preconditioner. So we can see here BiCGStab on 1 and 8 processes, and our implementation that was running also on, I believe, on 8 processes, and then we were using Skylake nodes. So we can see here residual versus number of iterations, and we can see that we got a slightly faster convergence compared to the BiCGStab implementation. So it's here what we can see also surprisingly is that on 8 processes we actually took a bit longer time to converge. Then another matrix that has more non-zeros, like almost 19,000 non-zeros, the convergence situation looks a bit different. We are sort of this was used with preconditioner. We are trying to converge, and then finally we are converging rapidly. And here the difference actually can be much clearly seen. So the idea is actually the message here. Although we may spend more computation cycles, but for some situations we can get actually up to 10 to 15% faster convergence. In regular cases, in majority of cases, we are in the same range, but for some we can actually get faster convergence. We have not understand the pattern yet, but we are on the way for that. Then the other, what we did is actually performance, and for performance we choose the biggest matrix that we were dealing with, so it's all 4.4 million non-zeros, and here I present sort of average time at first versus number of MPI processes. So we were using as much as we can 28 MPI processes, so pinning one process to one core, and we can see that at the beginning the execution time is actually 0.4 seconds. So it's still too low for scaling. We need to have in the range of 10 seconds or about a minute of original implementation in order to see scalability. It scales very well it drops very well in terms of performance from 2 to 8 processes, and we can see even here, and then it actually convergence slightly decreases because there are not enough computations to be done. So it's actually you see it actually flattens a bit. We also did some normalization, and we tried to compare to see the difference, to see actually the overhead and normalization against original execution time. And what we can see over here is that we see a slightly faster execution for FFP implementation, and so it starts from 2.7 times to 2x overhead, while pure AX Plus implementation starts from around 3.4 and drops until 2.4. So it's actually some improvements as well, and note that scalability is actually looks smooth here because we have a lot of computations to be done. In terms of convergence results, I would like to prove you that with BiCGStab we are also getting a very good residual on every iteration. So this is for the example of another matrix, and here condition number is 10 to the power 3, and we have 14,000 non-zeros. We compared again against MPFR implementation, and AX Plus and FP implementations always deliver the same results, while we already start seeing the difference between on 1 process and 8 processes. So this is the difference actually propagates over here. So just to conclude this presentation, so the idea here is to create a general framework for reproducible Krylov solvers based on what we already had, what we already seen at PCG, and to propagate it explicitly to BiCGStab. We rely on algorithmic and programming strategies, and we demonstrate this approach on PBiCGStab, where all inner products, all operations are correctly rounded on every stage. We can see that the overhead can be as low as 2x overhead, and we expect when we will go on large-scale computations using multiple nodes, and the overhead can even drop. We see this from PCG implementation, and then our code is available here on GitHub. And the future work, we are focused on larger runs, applying different preconditions, as well as using GMRAS, which is a bit more complex solver. And we are also focused on pipeline solvers that actually have very known issues of accuracy problems. So we hope to get some work done there and hope to stabilize the solvers as well. So thank you very much for your attention, and I'm looking forward for your